Welcome back to the Deep Dive, where we take a stack of your sources and extract the most important nuggets of knowledge. Today, we're plunging into a topic that's, it's quickly becoming central to how we interact with AI, agentic AI applications. Imagine giving your AI system not just the ability to talk, but, to actually act in the real world, to perform tasks, make decisions, even manage other systems. It's this incredible leap in capability. But, as you might guess, it comes with an equally monumental leap in security challenges. It's transforming our familiar digital threats into entirely new frontiers.
Precisely. Yeah, it's a big shift. Our source for today's deep dive is the Comprehensive Securing Agentic Applications Guide 1.0. It's from the OWASP Gen AI Security Project, and it's hot off the presses, published just this July 28, 2025. So our mission today is really to unpack what makes these applications unique, identify the new attack surfaces, and most importantly, explore the practical, actionable guidance for securing them. Because AI isn't just generating text anymore, it's taking action.
Okay, so let's unpack this then. What exactly makes an AI application agentic? What makes it fundamentally different from, say, just a chatbot we're used to? What are the building blocks here?
Right. At their core, agentic applications are built from several key components, or KCs as the OWASP guide calls them. They all work together. They give the AI its ability to, reason, plan, and act. First up, we have KC1, generative language models.
The brain, basically.
Exactly, the brain of the operation. Think of models like GPT-4, Claude, Gemini, but it also includes smaller, specialized models, SLMs. And even multimodal LLMs that can handle images or audio. Now, these models are often fine-tuned for specific tasks. That boosts performance, sure, but it can also introduce some subtle new security issues.
Okay, so a powerful, maybe specialized brain. How does that brain actually decide what to do? It's got all this intelligence, but then what?
Yeah, good question. That's where KC2 orchestration comes in, or control flow mechanisms. This dictates the agent's overall behavior, how it decides the sequence of tasks. It could be a simple workflow like a predefined list of steps. Or it could be something much more complex like hierarchical planning.
Hierarchical?
Yeah, where you have a central orchestrator like a manager breaking down a big goal for specialized sub-agents. Or you might even have multi-agent collaboration. That's where multiple AI agents work together more like peers, sharing info to hit a common objective. It's basically the agent's internal project manager.
Okay, so we've got the brain, KC1, and the project manager, KC2. But how does it actually think through complex problems, the ones needing multiple steps?
Right, that's KC3, reasoning planning paradigm. This is how the agent, thinks and solves those tricky multi-step tasks. You've probably heard of chain of thought. COVT.
Yeah, where it kind of talks itself through the problem.
Exactly. The LLM breaks it down step by step. Or there's tree of thoughts, 2T. That explores multiple reasoning paths at the same time, sort of like brainstorming different solutions and evaluating them. It's about giving the agent problem-solving strategies, not just raw knowledge.
Makes sense. And these agents, they need to remember things, right? What they've done, what they know, who they're talking to, how do they keep track?
Absolutely. That brings us to KC4, memory modules. Super important for coherent interactions for personalization. An agent needs to retain information. This can range from simple in-agent session memory, just for that one interaction, to something like cross-agent, cross-user memory.
Whoa, shared memory.
Yeah, shared across multiple agents, multiple users even. And as you can probably guess, the level of shared memory drastically impacts security. Potential data exposure goes way up. Think of like a vector database acting as the agent's long-term recall. It's like an external brain supplement.
Okay. And finally, the whole point is that these agents are designed to act. So how do they go from generating text to actually, doing things in the real world?
That's KC5. Tool integration frameworks. This is where the magic happens, where the agent gets its ability to act beyond just words.
Yeah.
These frameworks let agents use external tools, things like APIs, functions, maybe databases.
To actually interact.
Exactly. To interact with the real world. You might have open source libraries like LangChain or Crew AI, maybe managed platforms like Amazon Bedrock agents. These frameworks are basically the agent's toolkit. They manage how it picks and uses those external capabilities safely. Or hopefully safely.
So it's got the brain, the planner, the memory, the toolbox. But where do those tools actually connect? Where does the digital meet the physical or the operational systems?
That's KC6, operational environment, sometimes called agencies. These are the external systems the agents directly interact with using their tools. This includes things like API access, obviously, but also code execution.
Wait, running code generated by the LLM itself?
Yes, potentially.
Yeah.
Also database execution, web use, like actually operating a browser. Even controlling PC operations, accessing file systems. And it can get really serious, operating critical systems like SCADA controls.
SCADA, like power grids, industrial stuff.
Exactly. Power grids, water treatment plants, industrial processes. Imagine a compromised AI getting access there. The risks jump from data breaches to potentially causing physical disruption. Real-world harm. Each one of these connections, KC6, it opens up a whole new frontier for security risks. It turns the agent from just a chatbot into a powerful, real-world actor.
Wow. That really drives home how high the stakes can get. Yeah. These components sound incredibly powerful, but also, kind of terrifying from a security standpoint. Where do things get really critical when we talk vulnerabilities?
You're absolutely right to ask that. Each of these key components, these KCs, introduces specific attack surfaces, and the OWASP guide maps out unique threats for them using these T codes to give us a common language. So, for example, with LLMs, KC1, we see risks like T5, cascading hallucination.
Cascading hallucination.
Yeah, imagine an agent confidently believes some completely made-up information, acts on it, and then that bad info spreads through its reasoning, its planning, its options. It could lead to, disastrous outcomes. Or there's T6, intent breaking. This is where the core decision-making of the LLM gets subtly manipulated. It might start pursuing unauthorized goals, even malicious ones, without anyone noticing right away.
So the brain itself can be tricked, its core purpose gets subverted. That's unsettling.
It is. Then with orchestration, KC2, you worry about T13, rogue agents. Picture a system with multiple agents, right? If one gets compromised, it can go rogue. Disrupt the whole system, send bad commands, corrupt messages between agents. And in those multi-agent setups, T9, identity spoofing is a big one too. An agent impersonating another. Big trust issues, unauthorized access.
And the actual thinking process, the reasoning, can that be attacked?
Oh, yes. Reasoning planning, KC3, can be attacked to directly manipulate the goals. That's T6 again. Or T8, repudiation, where the decision trail gets obscured, makes it incredibly hard to figure out why an agent did something, or even if it went off track. This can lead to T7, misaligned behaviors that you don't spot until it's way too late.
And memory, I bet that's a huge target, especially with that shared memory idea.
Huge target. Memory modules, KC4, are vulnerable to T1, memory poisoning. This is where someone injects bad data, malicious data, into the agent's memory. It affects current and future decisions, like slipping a false fact into its long-term knowledge. And if that memory is shared across agents or users, you get T3, privilege compromise, through unauthorized data access. The risk just amplifies.
Okay, so messing with its memory could make it do almost anything. What about those tools it uses to act? KC5.
Right, tool integration frameworks, KC5, they face T2, tool misuse. This happens when unverified, maybe untrusted, or even compromised tools get exploited. The agent gets tricked into using them in ways they were never meant for. And critically, there's T11, unexpected remote code execution, or RCE.
RCE. That sounds bad.
It is bad. If a tool enables unintended code execution, a seemingly harmless tool call could suddenly turn into a full system compromise. It's like you give your AI a hammer to build a birdhouse, but it ends up, tunneling into the bank next door.
Okay, this is where the rubber truly meets the road, isn't it? The operational environment, KC6.
Absolutely. KC6, the operational environment, those direct links to the real world, they present the highest risks for T3, privilege compromise, and T11, unexpected RCE. Especially in environments with loads of access, full code execution capability, control over critical systems. If an agent with access to, a financial system or industrial controls gets compromised, the impact isn't just data loss, it's direct financial or physical harm. These environments can also be directly misused. T2, overwhelmed with requests causing denial of service. T4, used for communication poisoning. T12, or even used to launch those rogue agent activities. T13.
Wow, okay. That really highlights this intricate dance between adding powerful features and managing the security risks, especially if you're building these things yourself. And, for developers trying to navigate this really new frontier, having reliable tools is absolutely crucial for securing these complex apps. Which actually brings us to a good moment to thank one of our sponsors, vibehack.dev. They provide a suite of developer-focused security tools designed specifically to help you build resilient agentic applications. They help secure your code and your environment throughout the whole development lifecycle. Definitely check them out at www.vibehack.dev.
So, okay, we've seen the components, we've seen the scary threats. What does this all mean for someone actually building or securing these systems? The OWASP guide isn't just pointing out problems, right? It's about solutions, actionable stuff.
That's exactly right. It's very focused on solutions. Building secure agentic systems means embedding security from the absolute ground floor across the whole development lifecycle. The guide starts with core security patterns. These are like fundamental building blocks, useful no matter what specific framework you're using. There's the tool use pattern, which is all about making sure the agent picks and uses external tools safely. The reflection pattern is really interesting, agents evaluating their own actions and correcting errors securely, self-correction. And the retrieval augmented generation, or RAG pattern. We hear about RAG a lot, enhancing LLMs by pulling info from an external knowledge base. But that introduces risks like data poisoning, T1 again, in that knowledge base itself. Then the guide gets into how different architectural choices really change your security needs. A sequential agent architecture might be simpler, linear, maybe one LLM, easier to secure in some ways. But then you have hierarchical agent architecture with that central orchestrator and specialized subagents, more complex interactions, or even a collaborative agent swarm, multiple peer agents working together. Lots of communication channels to secure. The guide uses a case study, a multi-agent co-pilot, using hierarchical planning to access things like enterprise calendars, email, Slack. Each of those API access points, KC6.1.1, even with predefined calls, is a potential risk that needs careful thought and management.
That makes total sense. The more complex the architecture, the more moving parts, the more places for things to go wrong. So what about the specific developer guidelines? What should people actually be doing day to day when building these?
Right. The guide provides really comprehensive agentic developer security guidelines across the lifecycle, starting in the secure design and development phase, laying the foundation. System prompt engineering and hardening is huge here. Absolutely crucial.
The prompt itself?
Yes. Defining the agent's core instructions securely. You need really clear boundaries, explicit DOs and don'ts, and robust defenses against prompt injection. That means using things like delimiters in the prompt, few-shot examples to guide behavior, maybe deterministic controls to really limit what the agent can access or do, trying to prevent it being tricked by malicious inputs.
So basically, trying to make the AI's core instructions as unhackable as possible, locking down what it should and shouldn't do from the very beginning.
Precisely. Then you've got standard, but still vital, secure coding practices. Things like rigorous input validation for all inputs, not just the arguments going into tools. Robust error handling that doesn't accidentally leak sensitive info. Secure key management seriously. No hard coding secrets, ever. And always the principle of least privilege. Components should run with the absolute minimum permissions they need, nothing more. Human in the loop, HITL, design is also key for many applications.
Having a person approve certain actions.
Exactly. For high-impact stuff, sending emails, modifying databases, spending money, human approval should probably be mandatory. It's a critical backstop against rogue agent actions. And you need strong rate limiting there, too, so the human isn't just overwhelmed with requests, like a denial of service attack on the approver.
That's a really important safeguard, yeah, especially with these powerful autonomous agents.
Absolutely. Then there's memory security design. Protecting the agent's memory, short and long term, like those vector databases we mentioned. This means strict access control, encryption, definitely validating data before you store it in memory, and PII detection and redaction. And alongside that, input-output validation and sanitization design, using AI guardrails.
Guardrails.
Yeah, on both inputs and outputs, to identify malicious prompts coming in or sensitive or harmful content going out. This also involves strict schema enforcement for tool arguments and outputs, like forcing things into a specific JSON structure. That reduces the risk of the LLM misinterpreting things or hallucinating unexpected formats that break downstream processes.
Okay, so building in the rules, the checks, the safety nets right from the very start. What about when you're actually building and deploying?
Good question. In the secure build and deployment phase, you're looking at things like static analysis, SAST, and dependency scanning, SCA. Integrate tools like Bandit or Snake or others into your CI/CD pipelines. Catch vulnerabilities early in your own code and in the third-party libraries you're using. And crucially, environment hardening and sandboxing is vital.
Sandboxing, isolating the agent.
Exactly. Isolate the agent's execution environment. Use containers, VMs, maybe WebAssembly. Limit the blast radius if it does get compromised. This is especially important if the agent is generating and running code. You really don't want it escaping its sandbox. You also want to prevent the agent from being able to modify the very pipeline that built and deployed it. And for runtime security, there are methods emerging, like Google's Camel framework was mentioned in the guide. The idea is to separate the control flow generation from the processing of untrusted data, trying to prevent malicious data from directly influencing agent actions at runtime.
Makes sense. And security obviously doesn't stop once it's deployed, right? It's got to be ongoing.
Oh, far from it. Deployment is just the beginning in many ways. In the secure operations and runtime phase, continuous monitoring and anomaly detection is absolutely key. You need real-time monitoring, looking for jailbreak techniques, policy violations, checking for PII in inputs or outputs, spotting unusual tool use patterns. This might include pre-execution checks before an action is taken or runtime monitoring inside those sandboxes for any forbidden actions. Then you have runtime guardrails and automated moderation.
More guardrails.
Yeah, but operating dynamically at runtime. Enforcing policies on the fly, maybe blocking or sanitizing inputs/outputs that look suspicious. And the guide makes a really important point here. The proximity of the guardrail to the application code and the LLM really impacts how effective it is.
Proximity, what does that mean?
Well, like a guardrail sitting way out on the network edge might miss subtle, multi-turn prompt injection attacks that build up over a conversation. So embedding guardrails closer, maybe within the application itself or even within the agent's code space, gives them better visibility into the context and makes them harder to bypass.
Okay, so it's not just if you have guardrails, but where you put them matters a lot.
Exactly. And finally, maybe most importantly for operations, logging, auditing, and traceability. Critical. Absolutely critical. You have to log everything. The reasoning steps, the generated plans, the tool calls, any HITL decisions, errors, state changes, all of it. But, and this is a huge but, you must never log sensitive information directly. No actual session IDs, no access tokens, no unmasked PII in your logs.
Why not? Isn't more data better?
Because the logs themselves can become a target. If an attacker gets access to your logs full of sensitive data, you've got another massive breach. So the guy emphasizes needing immutable logs that can't be tampered with, and strict least privilege access to the logging platforms. It also mentions purging memory context if the data subject changes to avoid leaking information from one user's session into another's logs.
Okay, wow. So after all that rigorous design, development, deployment, monitoring, how do you really know? How do you know your agentic application is actually secure? Especially with these systems being so dynamic, adaptive, how do you get that assurance?
Yeah, that's the million-dollar question, isn't it? Knowing they're secure requires active assurance. It's not just build and forget. And that's where red teaming and behavioral testing come in, big time. Red teaming agentic applications means simulating real adversarial attacks.
Like penetration testing, but for AI agents.
Kind of, yeah. But specifically targeting these new vulnerabilities. Things like prompt injection, trying to escalate privileges, poisoning the memory, finding weaknesses traditional testing might miss. There are frameworks starting to emerge just for this. Agent Dojo, Agentic Radar, Agent Poison were mentioned. They're designed to test things like tool calling manipulation, memory contamination. It's about proactive, continuous testing, deliberately trying to break the agent in clever ways.
So you're basically hiring digital saboteurs or building your own to try and trick your AI, expose its flaws before the real attackers do.
That's a pretty good way to put it. And then, alongside that, you need behavioral testing for agentic applications. This goes beyond just looking at the code or trying specific attacks. It evaluates the agent's actual actions and interactions across a wide range of scenarios. There are benchmarks like Agent Bench, assessing task-solving abilities, or HALE-MM, evaluating things like accuracy, robustness, fairness, even toxicity. The goal here is to uncover hidden problems. Maybe the agent does something completely unexpected or develops harmful goals, even if the code looks okay and it resisted the red team's specific attacks. You might code something perfectly right, but if the AI's behavior in the wild is still wrong or dangerous, that's a whole different kind of failure.
That makes perfect sense. It's not just about the code, it's about the outcome, the actions. And tying all this together for accountability, how do you know why it did what it did?
That's where explainability audits become crucial. Understanding the why behind an agent's decision. Techniques include using chain of thought, like we discussed, to get insights into its reasoning process, employing that human-in-the-loop oversight at critical junctions, and going back to logging, rigorously logging agent-to-agent negotiations, tool interactions, everything. It's all about ensuring traceability and accountability. So you can track which permission sets were used, which identity the agent thought it was acting as, understanding the chain of events. Ultimately, all these security measures, from the secure design patterns through development, deployment, monitoring, red teaming, explainability, it's all aimed at one thing: ensuring that these incredibly powerful AI systems operate safely, reliably, and importantly, comply with the evolving regulations around AI.
And speaking of compliance and managing AI risk, That's a perfect time to thank our other sponsor, compliance.aristesis.com. They specialize in helping organizations navigate the really complex landscape of AI risk assessment and regulatory compliance. They provide tools and expertise to help ensure your AI deployments meet the highest standards for safety and governance. You can learn more about what they do at compliance.aristesis.com.
Wow, okay, what a deep dive that was. It's abundantly clear that agentic AI applications, they represent this monumental leap in capability, absolutely. But they also bring this whole new paradigm of security challenges with them. From hardening the LLM's brain to safeguarding its memory, controlling its actions in the real world, securing these systems really demands a holistic, lifecycle-based approach, doesn't it?
Absolutely, 100%. The OWASP guide makes it crystal clear. Security is not an add-on here. It's not something you bolt on at the end. It has to be about proactive design from day one, continuous vigilance throughout the lifecycle, and, honestly, a fundamental shift in how we think about trust and control when it comes to autonomous systems. It's about building agents that aren't just intelligent, but also inherently trustworthy and safe.
So thinking about all this, what does it mean for you listening? As these AI agents become more sophisticated, more integrated into our daily lives, into critical infrastructure, consider how these foundational security principles we've talked about today for agentic systems might actually transform our understanding of digital security across all connected systems in the future. As AI capabilities get even more deeply embedded everywhere, what new questions does this raise for you about trust, about autonomy in a world that's being increasingly shaped by AI? Thank you so much for joining us on this deep dive. We'll catch you next time.